Welcome back to the deep dive. So, I want to start with a scenario. A scenario I think most of us have been in, even if we didn't really notice the complexity behind it.
Okay.
You're walking through, say, a mechanical room, and you see a gauge. Just a simple round dial with a needle.
The classic pressure gauge. Yeah, I can picture it.
Exactly. And the needle points to a number, let's say 50 psi. You look
Right.
at it, you nod, and you trust it. But today, we're going to kind of shatter that trust a little bit.
Just a little.
Because how does that needle actually know to point to 50?
That is the million-dollar question, isn't it? We live in this, digital age. We assume everything is just a sensor talking to a microchip.
Right, there's code somewhere doing the math.
But in a huge part of the industrial world, I'm talking refineries, power plants, that number, it isn't coming from silicon. It's coming from geometry.
A physical fight between pressure and metal. We're looking at a stack of training documents for instrument technicians, specifically on link and lever systems. And I have to admit, when I saw that title, I thought, okay, levers, third grade science.
Simple machines, right?
Mhm.
Fulcrum, load, done.
That's what I thought. But reading this is not a seesaw. This is about building an analog computer out of screws and brass bars. It's about taking this messy physical force and translating it into a precise linear number.
Analog computer is the perfect phrase because you have to remember, nature isn't linear. If you pump pressure into a metal tube, it bends. But it doesn't necessarily bend in this perfect straight line way that matches the numbers on the dial.
So the machine is sort of lying to you initially.
In a way, yeah. The raw physics is messy. The job of this link and lever system is to tame that physics, to use geometry to force the metal to tell the truth.
Okay, so our mission today is to unpack that geometry. We're going to look at the mechanics, learn the vocabulary, which is a language all its own, and then we get into the really mind-bending part. Calibration. How do you tune a piece of metal?
It's an art form. It really is.
So let's start with the hardware, the building blocks. The source material kicks off by defining the types of levers, and it starts with the single lever.
Right, which is your classic crowbar. You've got a bar, a pivot, the fulcrum at one end, and you apply force at the other.
And the text is pretty rude about it. It basically says they are not very useful.
It's harsh but fair. I mean,
Harsh.
think about it. In an instrument, if you push a single lever, it just rotates. It doesn't actually transfer that motion to anything else.
It's a dead end?
Exactly. To build a machine that calculates, you need a double lever.
Okay, so paint the picture for us. What makes the double lever the key?
Well, a double lever has an input point and an output point. So imagine a bar pivoting somewhere along its length. Force comes in one end, rocks the pivot, and pushes force out the other end. And this structure, this is what allows for the most important concept here, amplification.
Amplification. This is kind of like the gears on a bike then.
Very similar. It's all about ratios. So let's say you have a pressure bellows, the part that actually senses the pressure. It's stiff. At max pressure, it might only expand, say, a tenth of an inch.
A tenth of an inch. You can barely see that.
You can't. And if you hook the needle directly to that, the needle would barely twitch. You need that needle to sweep 6 inches across the face of the dial.
You have to turn a tenth of an inch into 6 inches.
Precisely. So by having a short input arm and a long output arm on that double lever, you trade force for distance. A tiny, tiny nudge on the short end becomes a massive sweep on the long end.
That's mechanical magic. You're magnifying motion without any electricity at all.
And it works the other way, too. Sometimes you have too much motion and you need to reduce it. It's all just a matter of where you put the pivot.
The source also mentions this isn't just about size, it's about direction. These instruments are crammed into tiny cases.
Oh, it's a packaging nightmare. And that's where directional changes come in. You have your standard 180-degree change, that's your seesaw. Push down here, it goes up there.
Standard stuff.
But then you have the 90-degree change. The L-shaped lever or the bell crank.
The bell crank.
Yeah, imagine an L bracket pivoting right at the corner. You push horizontally on one arm, and it pulls vertically on the other, lets you route motion around corners. It's how you fit all this into a box the size of a grapefruit.
Okay, so we have multipliers and steering. But this brings us to the part of the reading that, I have to admit, it made my brain hurt a little.
I think I know exactly which section you mean.
The distinctions between the types of levers, the physical lever, the actual lever, and the effective lever.
The effective lever.
Yeah. I had to read this 3 times, and I'm still not 100% sure I did it.
Don't feel bad. This concept is the gatekeeper. If you don't get this, you can't calibrate an instrument. But it's actually really intuitive once you visualize it.
Okay, Walk us through it. The physical lever seems obvious.
It is. That's the object, the piece of metal. It might be straight, it might be curved like a banana, it doesn't matter. It's just the hardware.
Okay.
And
The actual lever.
the actual lever is a geometric idea. It's the straight line drawn from the pivot point, the axle, to where the next link attaches.
So even if the metal itself is shaped like a pretzel, the actual lever is just the straight line as the crow flies.
Exactly. Physics doesn't care about the pretty shape. It cares about the distance between the pivot and the force.
Okay, I'm with you. Now, what is the effective lever?
This is the game changer. The effective lever is the imaginary line from the pivot that meets the connecting link at exactly a 90-degree angle.
A 90-degree angle. Why does that matter so much?
Well, think about pushing a heavy door. If you push straight at it, perpendicular, you're at 90 degrees. You get maximum leverage, right?
Right, it opens easily.
Now imagine standing near the hinge, pushing towards the hinge, almost parallel to the door. You're pushing hard, but the door barely moves.
Because all my force is wasted, it's not going into the rotation.
Exactly. The effective lever is just a way of measuring how much of that lever is actually doing work at any given moment. It's the perpendicular distance. And here's the kicker. As the lever rotates, that angle changes.
Wait, so if the angle is changing, the length of this effective lever is also changing.
Yes, that is the secret. As the machine moves, the lever that the physics actually cares about is effectively growing and shrinking in length.
That is wild. So it's a variable gear ratio that's changing as you use it.
Correct. And that means the amplification changes. This is why these instruments aren't naturally linear. They want to create curves.
So when I see a needle move smoothly from 0 to 100 in a perfect line, that's not natural.
No. That is a carefully engineered illusion. You have to arrange the links so that their changing geometries cancel each other out. You use one curve to fight another curve, and what you get is a straight line.
Wow. That gives me a whole new respect for a simple dial.
It is geometry taming physics.
Okay, so before we get to fixing these things, the calibration, we need to speak the language. The source has this whole glossary.
It has to. In this line of work, vague language gets people hurt. You have to be precise.
Let's look at range versus span. In normal conversation, I'd probably use those interchangeably.
Definitely not. Range is the territory. It's defined by the limits, the lower and upper range values. So for a thermometer, the range might be -20 to +100 degrees.
Okay. And span.
Span is the distance. It's just the math. Upper minus lower. So in our example, 100 minus 20 degrees. Range is where the fence is. Span is how big is the yard.
I like that. Okay, now let's talk about the enemy.
Error. Simple math. The gauge says 50, reality is 48, your error is +2. But the types of error are where it gets interesting.
The one that sounded like a medical condition to me was hysteresis.
It does sound like something you need a cream for. But in physics, it's basically energy memory. Hysteresis is when you get a different reading depending on if you're going up the scale or coming down it.
So if I pressure up to 50, the needle might land on a slightly different spot than if I go up to 100 and then come back down to 50.
Exactly. Think of a speedometer in a really old car. It gets sticky. That gap, that difference based on direction, is hysteresis.
What causes that?
Usually friction in the pivots, or the metal itself not springing back perfectly. It remembers where it came from.
That seems dangerous. You need to know 50 is 50.
Absolutely. If the hysteresis is too big, the part is trash. You can't calibrate that out.
And how is that different from deadband?
Deadband is just slop. Imagine the steering wheel on an old tractor. You can turn the wheel a few inches left or right, and the tires don't move at all.
I think I've driven that tractor.
We all have. In an instrument, deadband is that range where you can reverse the input, start dropping the pressure, but the output needle hasn't budged yet. There's play in the links.
So deadband is a lack of response. Hysteresis is a shifted response.
You got it. And both are the enemies of precision.
Okay, so we get the mechanism, we have the vocabulary. Now let's get to the boss fight of this deep dive. Calibration.
This is where the rubber meets the road, or I guess the screwdriver meets the screw.
The source lays out a scenario. Your gauge is wrong, it's lying to you, and it breaks the problems into 3 geometry errors. Let's walk through them.
Let's do it.
Problem 1, 0 error.
This is the most common one. It's what it sounds like. 0 pressure in the line, but the needle isn't pointing at 0. It's at 5 psi, or maybe below 0.
The whole scale is just shifted.
Right. The line on the graph is straight, the slope is right, but it's just starting the wrong place. It's like a ladder leading perfectly, but you need to just scoot the whole thing over.
And the fix.
0 adjustment. It's usually a simple micrometer screw right on the pointer. You turn it, the needle moves. You're not changing the leverage, you're just resetting the start point.
Okay. That feels satisfyingly simple.
It is. But don't get cocky, because next comes span error.
Okay, so scenario. I fix the 0, it's perfect. Now I pump the pressure up to 100%. But the needle only goes to 90, or it flies past to 110.
So the start point is right, but the total travel is wrong.
Exactly. The source calls this a multiplication error.
Right. Back to the ladder.
Yeah.
The feet are in the right spot, but the ladder is leaning at the wrong angle. It's not reaching the roof. You need to change the slope.
How do you do that?
You tune the levers. You physically change that ratio we talked about. Usually there's a slide on the lever. You loosen a screw. You slide the connecting link up or down the bar to change its length, and you tighten it again.
So you're literally changing the gear ratio.
Yes, you're span adjusting. If the reading is too low, you need more travel. So you lengthen the input lever to get more throw.
Okay, so 0 is set. Span is set. 0 is 0. 100 is 100. We should be done.
You would hope so.
Yeah.
But there is usually a third, more insidious villain waiting.
Angularity error.
This is the one that breaks people's spirits. This is when 0 is perfect and 100% is perfect. But then you check 50% dead center, and the needle is reading 55.
It bows. The line isn't straight, it's curved.
Exactly. And this brings us right back to that effective lever. The error happens because the effective lengths of the input and output levers are changing at different rates as they move.
So the multiplication factor isn't constant?
Correct. The system is nonlinear.
How on earth do you fix that?
You can't just slide a link. You have to change the angles. You have to adjust the linkage. So the starting angle of the levers creates a relationship where their effective lengths change at the same rate. You're trying to cancel out the curve.
But the source warns about something here. It says fixing angularity is messy.
It's the most frustrating part of the job because think about it. To change the angle, you usually have to lengthen or shorten a link. When you do that, what happens to your 0?
Oh, you just moved the needle, so your 0 is wrong again.
And what happens to your span?
You probably just changed the radius, so your span is wrong, too.
Exactly. It's like a waterbed. You push down one problem, and another one pops up. So you fix the angularity to straighten the line. Then you have to go back and fix 0. Then you check span, and you have to tweak that. Then you check angularity again, and it's probably slightly off now.
It's a loop.
It's an iterative cycle. The source calls it a repetitive cycle of adjustments. You spiral in. You loop through 0, span, and angularity until finally everything aligns.
It really sounds like tuning a musical instrument.
That is a fantastic analogy. It is tuning. You are mechanically tuning the geometry to produce a linear truth.
There's a diagram in here, figure 13, that shows the ideal setup. It's 2 parallel levers.
The parallelogram effect. If you can maintain that parallelogram shape as it moves, you get perfect linearity. But in the real world, with limited space, you rarely get that perfect setup. You're always just fighting to approximate it.
It's amazing to think that all this is going on inside a simple gauge. But the source mentions these are also used in controllers. These things are actually controlling processes.
Absolutely. This isn't just for display. In a pneumatic controller, this system isn't just moving a needle, it's moving a valve that controls the pressure in a massive chemical reactor.
So if you have slop or deadband in that linkage,
Your control system gets sloppy. Imagine driving a car on a winding road, but your steering wheel has a 2-second delay. That's deadband.
that's terrifying.
In a factory, it's the same danger. A reaction gets too hot, but the controller doesn't realize it because of the deadband in the levers. By the time it catches up and opens the cooling valve, it might be too late.
So that slop isn't just an annoyance, it's a safety hazard.
Precisely. That's why technicians spend so much time on this. It's operational safety. It's about preventing explosions.
To bring this all together, we have these analog computers. They use the geometry of effective levers to amplify and linearize motion.
Right. They turn curves into straight lines.
And we have a specific language range, span, hysteresis, deadband to describe their behavior.
And angularity, the curve that haunts our nightmares.
And then the calibration process, which is this 3-part harmony of fixing 0, span, and angularity, all while trying not to mess up the other 2.
It is a cycle of refinement. You spiral in towards accuracy. You never get it perfect on the first try.
It really makes you look at a simple pressure gauge differently. I'm going to see one and just imagine all those little bars inside fighting to keep that line straight.
It is an elegant solution. We think of tech as silicon and code, but this is high technology. It's just mechanical technology. It's cleverness in brass and steel.
It's the geometry of accuracy.
Exactly.
So, as we wrap this up, I want to leave you with a thought. We live in a world of auto-calibrate buttons. You buy a digital scale, you turn it on, it says CAL, and it just zeroes itself. We assume truth is automatic,
We do. We take it for granted.
but in this link and lever world, truth, the accurate measurement, is something you have to physically build. You have to tune it. You have to maintain it.
That's very true.
It makes me wonder, do we lose a fundamental understanding of what measurement actually is when we stop having to physically tune the geometry ourselves? When an algorithm handles the linearization, do we forget that the world isn't naturally linear to begin with?
That is a profound question.
Ah.
When you tune the mechanism, you understand the forces, you understand the error. When you just read the screen, you just trust the number. And maybe we trust the number a little too much sometimes.
Something to think about the next time you trust a digital readout without a second thought. Thanks for listening to this deep dive into the hidden mechanics of the industrial world. We'll see you next time.